Hello, in the last videos we discussed many problems of DSU. Let's discuss the next one. Here is the question, read it and give it a try. You are given a weighted undirected graph with n vertices 1 to n. Initially G has no edges. You will perform m operation to add edges to G. The ith operation is as follows. You are given a subset of some vertices consisting of k vertices. For every pair, add a edge between U to V with weight Ci. After performing all m operations, determine whether G is connected. And if it is connected, find the total weight of edges in the minimum spanning tree of G. And the constraints are n, m, k are up to 2e5 and the values of C are up to 1 in n. So before solving this, let's see what is MST. So MST is the minimum spanning tree, and what is this for a graph? It is simply the subset of some edges such that the graph is connected. So let's say we have a graph with 10 vertices and we have 20 edges. MST will be the subset of some edges such that the graph will be connected. And for n nodes, what will be the number of edges in the MST? It will be n minus 1, because in a tree with n vertices, the number of edges that we require are only n minus 1, that is 9, so that the tree is connected always. Similarly, for any graph of size n, the MST will be of edges n minus 1, so that only n minus 1 node edges are required to connect all the vertices in the graph, so that making a single connected component. And what is minimum? So let's say this is a weighted graph. So minimum spanning tree is simply the subset of some edges such that the total sum of subset of edges we selected is the least and the graph must be connected. So it is simply MST. For example, we have 1, 2, 3 and we have edge between these are also. The weight is 3, 4, 5. So what will be MST of this graph? It will be simply 3 and 4, because for graph of size 3 nodes we require only 2 edges. So we want the minimum as well. So for now, let's assume the least two we are selecting. So 3, 4. And after this, both the graph is connected and it is minimum as well. So the answer is 7. So this is MST. And now coming to original problem. Let's say this is the given input. So 4 is the number of nodes in the tree in the graph, and 3 is the number of operations or queries that we are given and we have to perform. So coming to first one. So 3, 3. It means that for every pair of 1 to 3, add an edge of size 3. So 1 to 2 add 3, 1 to 3 add 3, and 2 to 3 add 3. And coming to 2, 2 and 1, 2. So just add an edge between 1 and 2 with edge 2. So 1 and 2 and edge 2. And coming to next one, 1, 3, 4. So add between 1 and 3, add between 1 and 3, 1 and 4, and 3 to 4. So in this way, for every n vertices, we are adding every edge that are possible from this with the edge of given value. And after that, finally, we have to find the MST. So for this graph, what will be MST? So from before we discussed that we have to select only 3 edges such that sum is least and the graph is connected. So let's assume that after some subset selections, we got this one such that the graph is connected and the weight is least also. So what will be the answer now? It will be simply 2 plus 3 plus 4, which is 9. So return 9. So how can you do this? So let's assume the least possible case for now. So the minimal case that can be the question is, there are 4 nodes and there is only one operation to perform, and it is simply add every node between 1 to 3, 4, add every edge between 1 to 3, 4, and with the weight of A, with weight of A. So what will be after adding? So for 1 to 2 add A, 1 to 3, 1 to 4, 2 to 3, 2 to 4, and 3 to 4. So we have A to the every edge possible, and now we have only one operation, so we have completed the operation. And now what will be the answer? So we complete the operation. So now we have to reduce the number of edges we have. So what should be the final number of edges in the MST? It should be 3, because we have 4 nodes. So the edges should be 3. And but now we have how many edges? We have 6 edges. So now we have to remove 3 edges such that the MST will be formed. For now, let's assume that these are some of the MSTs that are possible. By removing 1, 4, 2, 3 and 2, 4, we can get this new one. And by removing 1, 4, 2, 3, 1, 3, we can get this one. So what will be the answer? In the answer, just we have to return the total weight of edges, right? So even in this case, the answer is 3a. And even in this case, the answer is 3a. So for now, we will simply return 3a, because any of the configurations, the answer is 3a. So instead of which configuration we are selecting, we just want the answer. So simply return 3a. Okay, so we found that for a single operation, the final configuration is independent, but the answer is fixed for everything, because for answer for this is also 3a, and the answer for this is also 3 as well. So from this we got that it is independent of the final configuration, but only the answer is required. But now let's say we have next operation. So in next operation we have only one operation 3 5, and we should add edge of b of weight b. So this is the first configuration that we have selected, and this is the second one. So this one and this one, and I'm considering this both again. And now we are trying to add 3 5 with edge weight b. So let's temporarily assume that we are adding 3 5 now for now, and the weight is b. And similarly we are adding 3 5 b 3 to 5 with edge weight b for temporarily for now. So these two are the cases. But now initially the answer is 3, right? But now what will be the answer? So if we clearly observe, even now the answer is 3a plus b, regardless of the combination, because anyways the final edges are same, because even the edges here are 4, and the nodes are 5. So this is obviously a correct MST, correct spanning tree, not minimum. Let's come to minimum now, because obviously for vertices of size 5, 4, we can have many spanning trees of size 4, but now we want the minimum one. But because this is one of the possible MST, this is one of the possible solutions of MST, and similarly this is one. What will be the answer for this? It will be simply 3a plus b, because a plus a and plus b. So it will be 3a plus b, and now also it is 3a plus b. So even now the answer is independent of the configuration, but now it is simply the answer, and this is same for every configuration as well. But what if a is least, for example? So from now what we got? So we got that we just need the edges but not the configuration, because the answer is going to be same for all. So we may got an idea now what. So we can simply instead of adding everyone, we can add only the set of nodes minus one edges. So but what if a is least and all other edges are very more? So for example, what is the observation that we came till now? So the configuration is independent, the answer is only important. So why we are not adding edge between 1 and 3? Why only we are adding between 1, 1, 2, 2, 4 and 3, 4, and why not 1 and 3? But what if let's say a is 1 and any other weight edge given is more than a? So then we can try to attempt to add this as well, because a is least. We want the least minimum spanning tree. So instead of wasting a, why not we just add a also, because this is least among all the edges. So what I'm saying is, let's say this is the original one. Initially we took only 1, 2, 1, 3 and 3, 4. But now let's assume we are taking a as a also. Why? Because let's assume a is least and all other edges are very more. So for 3 to 5 the edge weight is 100a. So instead of considering this, why not consider the least edge, which is a? Anyways, adding edge between 2 and 4 is redundant, because obviously by adding 2 to 4 it is just becoming the extra edge but not replacement, because initially we selected 1 2, 1 3 and 3 4. So from this we got MST, but now we are thinking that A is least, and why not we are adding 2 to 4 also, because A is least. We cannot add it is least. We can add only if it is useful, right? So 2 to 4 is useless, because even without 2 to 4 we got MST. But what if we are not trying to add 100A and we are trying to add A? So without 100A it is not possible to make MST, because obviously we have to make the tree connected finally. So instead of adding 3 to 5, which is high value, we cannot add A, because even if we add A, we are unable to combine these both connected components, because we are unable to make path between 3 and 5. So which is the ultimate condition of MST. So in MST, every edge should be reachable by any other. But by greedily, if we are trying to add A instead of 100A, we are unable to make a single connected component. So obviously we cannot go by think that A is least, so we will add all edges with a with weight A. So and now, so it is guaranteed that it is better to take only some particular edges of every query. So let's come to original query again. So from the observation still now what we have decided. So for 1 2 3 4, we can add between 1 2 1 3 1 4 2 3 2 4 3 4, and instead of that it is just enough to make any 3 edges from this, right? Because we came from a single example. So for a single operation, what is the optimal answer? It will be simply considering 3 edges, only 3 edges, because the number of vertices are 4. So we are generalizing this not only for single operation. So we are considering now that if we have many operations, for every operation we can consider only the nodes minus 1 number of edges that are being added to the graph regarding this operation. So hope you got this, because let's say this is the first operation, and second operation is also adding the edge between 2, 3 and 4 with size b. So instead of adding between every pair, why not we add only the nodes minus 1 number of edges, whether they are any edges, because we can add between 1, 2, 1, 3, 1, 4, or 2, 3, 2, 4, 3, 4. But only the important thing is we have to add only 3 edges to make the graph connected. And how we are sure that the answer will be correct, because from this example we got that the main requirement from this operation is to make sure that the only graph is connected and to get the minimum. And the final consideration that we are is we have to take any node minus 1 edges, so that every edge weight is same. So obviously our answer is going to be correct, because we are taking the optimal answer in every operation by adding only nodes minus 1 number of edges, but not between every pair of edges. So any nodes minus 1, for example, if the nodes is 5 in the operation, we can add edges between only any 4 pair of edges, any 4 pair of vertices, so that the trees connect, so that the graph is connected finally after operation. And also the weight is least possible, because every edge has same weight, whether it is a or b. So obviously it is going to be it is going to be satisfied every time. So any nodes minus 1 or any particular subject, so any nodes minus 1. So the main observation that we got till now is, for every operation, instead of adding edge between every pair of vertices, we can add edge between any node minus 1 number of vertices, so that it is connected and we will get the least answer as well. So why not simply add edges from first node? So let's say we are inputting kc, and k is the number of the number of vertices that we have to add edges, and c is the weight of the edge that we are going to add. So we are inputting the values, and we got that we are going to add k minus 1 number of vertices, k minus number of edges, because the number of nodes is k, so we only want k minus 1 edges. So instead of selecting some random edges, why not we simply add between 1 to every other node, the first node in the graph to any other. So it will be simply k minus 1. So simply we can push back c comma make pair of. So it simply represents that the edge between v0 minus 1 node and vn minus 1 node with a edge weight of c. So till now we simplified the question. So instead of adding the edge to every pair in the operation, we assumed we got an optimal answer for making this. And now what is left? So now we got a simplified graph, and now we have to find the MST of the graph. How can we do this? So let's say this is the graph formed after the operations doing optimally, and now we want the MST. So what is the number of edges that we want in final MST? It will be 4 here, because we have 5 nodes 1 to 5, so the number of edges required are only 1 to 4. And now we want the least answer. So what is the first idea that we can think? What if we select only the edges with the least weights of 4 count? So let's say we have 10 edges, right? So let's say we have 10 edges, and now finally we only want 4 edges, because only 4 is required for MST. So we want minimum answer. So why not take the edges with the least weight from these with 10 among these 10? So why not we just select least 4 edges from these 10 to get MST, because it cannot be optimal always, because the tree may not be connected after doing the operation selecting the least 4. For example, this is the graph. So for now let's assume that we want only 4 edges, and now coming to 4 edges, what are the least one? So coming to 2. So we are assuming that we are taking 2 because it's the least one, so add it between 5 4. And coming to next least one, which is 3. So let's assume we are adding this one, and also coming to next one, it is 3. It is 3, and we have made 3 edges. And coming to next one, the next one among 7 8 9, which is least, 7 is least. So now let's assume that we are making this as well. 4 to 2, we are combining this, and 3 is left because we did not add any edge with respect to 3. But is this a final answer? Because the number of edges we have taken is 4 so far. But is this the answer correct? No, because finally it is not connected. Though we got the minimum count, minimum weight of edges, but we did not make it connected. So obviously this is not the correct answer. So how can you do this? So now instead of blindly taking the least one, let's try to do dry run and let's see where we done the mistake. So coming to least one, so let's add 4 to 5. So let's add 4 to 5 for now. Let's add 2. And for 1 to 5, let's add 3 because this is the next least one. So coming to next one, 1 to 4 is least right. So now originally we are trying to make 1 to 4 as 3. We are combining trying to add edge between 1 and 4 with edge weight 3. But is this required? This is not required. Why? Because they are already connected. Because let's assume this is the inner subgraph that we are at. We already have edge between 1 and 5, 5 and 4. So obviously by these both edges, we can reach 1 to 4. There is no need of this edge, right? From this example, we discussed that we are simply adding a new edge, which is useless. Though this is minimum, it is not required to add because already we have connected these both, right? So why we again want an edge between these both? It is just a redundant. So don't add this edge. So just simply this by don't considering it. And now this is completed, and we are not adding it this one. And now coming to the next list one, which is 7. So 7 is between 2 and 4. So can we add between 2 and 4? We can absolutely add because these both are not connected till now. So combine this and add answer. And coming to next list one, it is 8. So coming to 2, 3. So can we add between 2, 3? Absolutely yes again because these are not connected before, and now we can connect these both. And coming to what are the number of edges we have taken till now? It is 4, and which is what we exactly require. So we got the answer. So in this case, by this we found that we got the minimum answer as well, and we made sure that the final component is connected as well. But now how can I do this without just adding the blind list edges? How can I do? So before adding an edge, what we just want whether they are already connected or not. Because before adding 1, 4, we have to check whether 1 and 4 already in the same connected component or not. If they are same, adding the present edge is waste. So don't add. If they are not connected, then add the edge and make them connected. So this is what we want. So by BFS or DFS, it will take often to find whether they are in same component or not. So this is where exactly DSU comes in. So we can simply use a DSU and find whether they are already connected by using merge function in often. And then if they are connected, then don't add the edge. If not connected, add the edge and merge those both and combine. So in this way we got the answer. But what if the final graph is not connected even after we are assuming this? For example, we got only 1, 2, right? We have only one edge and we have 4 vertices. So we want the number of edges to be 3. But even after traversing the all edges, we will get only this edge. But this is not connected because we want three vertices, 3 edges. So just instead of returning answer, we will check whether the graph is connected or not before returning the answer. If the graph is connected, then return the answer we found so far. Else return -1 because we are unable to make the MST because there are no sufficient number of edges. So let's check the code. So initially I am inputting k and c, the number of vertices, and we are adding the edge weight because here we have to sort with respect to edge weights, right? Because we are traversing from least edge to highest edge. So it is better to store the first value as weight because then we can sort with respect to first one, and then we can travel the edges and we can do the operation. So we are pushing this into vector because it is better to sort as we have the first parameter as weight. So we are sorting both, and after this what we will get? We will get the weight. We will get the vertices pair such that the first one is the least weight so far, and the second one will be the edge connecting those both. So answer is 0, and now we are traversing the whole edges we found so far, and this is the edge weight. Distance is the edge weight, and F is the first node, that is the edge connecting to, and S is the second node, that is the edge connecting to. And now we are checking whether these both are not connected. So here the merge will return whether they are not connected. So let's say we are finding the parent of first and second. If the parents are equal, then return 0. If the parents are equal, it means that they are already connected. So we no need to add answer. But here we are checking whether merge of FOSS. So answer will be added, the distance will be added to answer only when merge will be 1. So when merge will be 1, it will be 1 when we are connecting and when they are not initially connected. So the merge function here represents whether they are not connected. If they are connected initially, then just return 0. If it is not, return 1 and merge these both as well. So if these are not connected, then add this to the answer, else don't add this to the answer and continue. So in this way we can find the answer by using merge function. And now we discussed that we have to check whether the graph is connected or not before returning the answer. So take a set and traverse all the vectors, all the nodes, and insert the ultimate parent. Because let's say we got this ultimate parent of 1 is 1, so find returns 1. Ultimate parent of 2 is also 1. The ultimate parent of 4 is 4. Ultimate parent of 3. So how can we check whether there is one connected component or not? So there can be only one component if parent of every node is the same node itself. So here, if we are inserting the parents of the all nodes into S. So finally, if size set is 1, it means that there is only one connected component. So if there is only one component, then return the answer. So return answer. If it is not 1, it means that there are at least two components. Because we got two ultimate parent nodes, so it means that there are two different components. So then return -1. In this way, we can return the answer. If you have any doubts, comment below. See you in the next video.